In this lecture video, we start looking at inferences about a single population proportion. In particular, we'll be looking at the developing hypothesis test about a single population proportion. In addition, we'll look at estimation of a population proportion, both or via a point estimate, but also via confidence interval estimation. And finally, we'll look at some sample size formulas that will allow us to construct confidence intervals with a given level of precision. So suppose that we have a binomial random experiment that we've described back in the module on probability and distribution theory, and that binomial experiment has n trials, each with success probability p, and that the random variable x is counting the number of successes in the sample. Then we know that the random variable x has a binomial distribution with n trials and success probability p. Now the proportion of successes in the sample will be denoted by p hat and is given by the ratio of the number of successes in the sample to the total number of trials. Now recall from our studies of probability, and in particular the module on sampling distributions and the central limit theorem, that for sufficiently large sample sizes n, the binomial distribution can be approximated by a normal distribution. Now this can be used to show that the distribution of the sample proportion p hat can also be approximated by a normal distribution. Specifically, the normal distribution with a mean of p and a variance of p times 1 minus p over n. And if you think back to Module 2 on sampling distributions and the central limit theorem, you'll recall that the last section in that module was on the normal approximation to the binomial distribution. And there our focus was on approximating the sampling distribution of x itself. But because the sample proportion is just x over n, we can use that information that we learned there to determine what we're saying here. And we did look at that. Actually, that was the first component that we looked at in that discussion, was the sampling distribution of p hat. And then from that, we got the sampling distribution of x, and that was our focus. But here, we're focusing on the sampling distribution of p hat itself, and we're going to be approximating that sampling distribution for sufficiently large sample sizes by a normal distribution with mean p and variance p times 1 minus p over n. And so based on that, we know that if we standardize p hat by subtracting off the mean of its distribution, which is p, and then dividing by, and I want to just point out here that we're dividing here not by the true standard error of p hat, but the estimated error of p hat. Notice up here that the variance of the sampling distribution of p hat depends on p itself. And if we don't know p, then we're not going to be able to calculate the variance. Therefore, we're not going to be able to calculate the standard deviation of p hat, which would be required to actually standardize p hat. So what we're doing here is we are calculating an estimated standardized version of p hat. We're subtracting off p. And I know that you're probably saying, well, look, if we don't know p, we can't subtract it off. That is correct. But what we're going to do is use this to come up with a procedure for example, for constructing confidence intervals for p. And so because of that, we would need to include p here in the numerator. You'll see how we do that in just a bit. We also use this or a similar quantity for constructing hypothesis tests about p. we're going to do something slightly different, though, in that context, because in the context of a hypothesis test, we have a hypothesized value of P, and we would use that in the denominator. So the quantity we have here is an estimated standardized version of P hat, where we are using an estimate of the standard error P hat here in the denominator. So we really have, we have an approximation. We're approximating the sampling distribution of P hat by a normal distribution with the appropriate mean and variance. But we also have an estimation step going on here because we're estimating the standard error. So we see here that this is not an exact distributional representation. This is an approximate. This is the approximate sampling distribution of this expression, this random variable, and it should be a pretty good approximation for large samples. So again, this is going to be the basis for hypothesis testing confidence intervals that we'll be looking at. And so let's start by looking at hypothesis tests, and we're going to go through the same kind of thought process that we have done for the other testing situations, where we look at a particular set of hypotheses that we are considering, and then we come up with a reasonable test statistic based on how we come up with a reasonable procedure, let's put it that way, reasonable rejection criteria, based on how the estimator, in this case P hat, behaves under the conditions of the null hypothesis versus how it behaves under the alternative hypothesis. And so when we're looking at this hypothesis test where P is equal to some specified value P0, P naught, and the alternative would therefore be the opposite of that the population proportion is not equal to that hypothesis value. And we are, again, we'll denote the significance level at which we're going to perform this test as alpha. And so how does P hat behave if the null hypothesis is true? If the null hypothesis is not true, how does P hat behave? In other words, what values of P hat would we expect to see if the null hypothesis were true? And what values of P hat would we expect to see if the null hypothesis is not true? And then can we use differences in what we would expect to come up with a procedure that would allow us to determine whether or not we think the null hypothesis or the alternative hypothesis is true. So if the null hypothesis is true, then the sampling distribution of P hat will be centered at the hypothesized value P0. On the other hand, if the alternative hypothesis is true, then the sampling distribution of P hat will be centered somewhere else. It'll be centered at P wherever P happens to be. P could be close to P naught, or it could be far away from P naught. But whatever the true value of P is, that is where the sampling distribution of P hat will be centered. And so then intuitively, values of P hat that are far away from the hypothesized value P naught will be evidence against the null hypothesis. So the question is, what values of P hat should be considered far away from P naught? Now, recall that for large samples, P hat minus P, and here we have the standardized version of P hat. And notice now in this situation, I don't have hats on the P, on P down here in the denominator. So this is the true standard error of P hat. Now, if we don't know P, which we won't know if we're performing hypothesis tests about P. Otherwise, if we did know P, we wouldn't have to test hypotheses about it. So we don't know this, we can't calculate this, but we can represent it. So that's the point here. So we know that for large samples, this is the true standardized version of P hat will be approximately standard normal. right? We know that. That's because of the central limit theorem. And so for large samples, if the null hypothesis is true, then the probability that we observe or that we obtain a sample for which p hat is between these two quantities, all right, will be approximately 1 minus alpha. Now again, we're calculating this probability, this probability uh, under the assumption that the null hypothesis is true, or in other words, we're calculating this probability um, under the conditions of the null hypothesis. And so if the null hypothesis is true, if p is equal to p sub 0, then that is why we're in this probability statement in these events we're using p0 instead of just p, because under the null hypothesis p0 is p. And so if the null hypothesis is true, what values of p hat would we expect to see with a fairly high probability? Well, values of p hat that are greater than or equal to that value and less than or equal to that value. All right, and the probability of our seeing values of p hat between those two quantities is approximately 1 minus alpha. And so therefore, by the complement rule, the probability of observing a value of p hat outside of that interval, either less than this quantity, I won't read that, but you can see it there, or values of p hat that are greater than this quantity, would be approximately alpha. And so this is going to lead us to a rejection criterion. We'll first state it in terms of an acceptance region and a rejection region. So for a fixed value of p sub 0, the values of p hat in this interval constitute the acceptance region. These are values of p hat that are consistent with the null hypothesis and therefore would lead to its acceptance. In other words, values of p hat in this interval would not lead us to reject the null hypothesis because they are consistent with the null hypothesis at a significance level of alpha. On the other hand, the complement of that set, the union of this interval and this interval, these are values of p hat that are inconsistent with the null hypothesis because values of p hat in those two intervals have just a very small probability of occurring, probability of alpha. All right, and so these are values of p hat that are inconsistent with the null hypothesis, and so therefore, if we observe a value of p hat in either of those intervals, then we would, as a matter of practice or as a matter of strategy, in determining which of the hypotheses to go with, we would reject the null hypothesis and conclude that the alternative hypothesis is true. Now we can restate this as we've been doing in terms of rejection rules, action rules, and so we would accept the null hypothesis, or in other words, we would fail to reject the null hypothesis if we observe a value of p hat greater than or equal to this quantity here and less than or equal to that quantity, and we would reject the null hypothesis and conclude that the alternative is true if p hat is less than this critical point or if p hat is greater than that critical point. Now, let's consider this left-tailed test, right? So the null hypothesis would be that p is greater than or equal to this hypothesized value, p0, and the alternative is that p is less than p0. Again, we will denote the significance level of the test by alpha. And so again, we ask ourselves the questions. How does p hat behave under the conditions of the null hypothesis? How does p hat behave under the conditions of the alternative? What values of p hat would we expect to see under if the null hypothesis were true? And what values of p hat would we expect to see if the alternative hypothesis were true? And so again, remember that regardless of whatever the value of p is, that is because p hat is an unbiased estimator of p, the sampling distribution of p hat will be centered right at p, wherever p happens to be. And so there will be a fairly significant probability of observing a value of p hat in the vicinity of p, wherever p happens to be. And so if p is greater than or equal to p naught, then we would expect to see larger values of p hat than if the alternative were true. And that's what we're saying here on the next slide. If the alternative hypothesis is true, then the sample proportion, p hat, would tend to be smaller than it would be if the null hypothesis were true, in that the sampling distribution of p hat will be centered at a value that is less than where it would be centered if the null hypothesis were in fact true. And so intuitively then, small values of p hat will be evidence against the null hypothesis. So the question is, how small does p hat have to be before we decide to reject the null hypothesis and conclude that the alternative is true? And so again, we are using this same approach, and we're going to come up with two probability statements. Notice that we have here, if the null hypothesis is true, and also we're assuming here that we have large samples so that these approximations are good approximations. Then if the null hypothesis is true, then the probability of obtaining a sample for which the sample proportion is at least this big. It's greater than or equal to p naught minus z sub alpha times the square root of p naught times 1 minus p naught over n. And again, this quantity here, this square root quantity, the square root of p naught times 1 minus p naught over n, that is the standard error of p hat on the boundary condition of the null hypothesis. All right, and so if the null hypothesis is true, then this probability is going to be approximately 1 minus alpha. By the complement rule, then, if the null hypothesis is not, we're still under the condition that it is true. So again, if the null hypothesis is true, then by the complement rule, the probability of observing a value of p hat that is less than this quantity will be approximately alpha. So again, that's by the complement rule. And so then that leads us again to partitioning the sample space of p hat into two sets, the acceptance region and the rejection region. The acceptance region is the set of values of p hat that are consistent with the null hypothesis, and therefore they would not lead us to reject the null hypothesis. We can also say that it would lead us to accept the null hypothesis, and again, we're talking about at a significance level of alpha. On the other hand, the complement of that set would be the set of values in the sample space of p hat for which we would reject the null hypothesis. Those values are inconsistent with the null hypothesis and therefore would lead us to reject the null hypothesis at a significance level of alpha. And so those are values of p hat that are in the open interval from 0 up to p naught minus z sub alpha times the square root of p naught times 1 minus p naught over n. Now again, we can reframe or restate this or put this in terms of decision rules. And so we would accept the null hypothesis if p hat is greater than or equal to this quantity, and we would reject the null hypothesis if p hat is less than that quantity. So accept the null hypothesis, or in other words, fail to reject the null hypothesis at a significance level of alpha if p hat is greater than this quantity, this critical point, and reject the null hypothesis at a significance level of alpha if p hat is less than that critical point. And finally, we can consider this test where the null hypothesis is that p is less than or equal to p naught. The alternative is that p is greater than p naught. And so again, how does p hat behave under the conditions of the null hypothesis? How does p hat behave if the alternative is true? In other words, what values of p hat would we expect to see if the null hypothesis is true? And what values of p hat would we expect to see if the alternative is true? And so if the alternative is true, if p is greater than the hypothesized value p naught, then the sample proportion would tend to be larger than it would be if the null hypothesis were true. In other words, if p is less than or equal to p naught. And again, this is because the sampling distribution of p hat is centered at p wherever p happens to be. And so intuitively then, based on this, large values of p hat will be evidence against the null hypothesis. And again, as always, the question is, well, how large does p hat have to be in order for us to reject the null hypothesis? And again, we use probability and probability statements about p hat to determine the appropriate critical point for this test. In other words, determining a critical point that will give us a significance level of alpha. All right, and again, that is based on probability considerations. And so you can see why we spent so much time looking at probability and in particular distribution theory, random variables and distributions, and then sampling distributions, because everything we do in terms of coming up with hypothesis tests and developing confidence interval procedures is based on probabilistic considerations. Even something like this, coming up with a candidate test statistic, in this case p hat, that's driven by considerations of distribution theory. We know that p hat is an unbiased estimator of p. And so we know that p hat will tend to take on values close to p. And so this is just, again, demonstrating why we spent so much time looking at probability and distribution theory, because that is the foundation of everything we do. It's the basis of everything we do in statistics. So if the null hypothesis is true, then for sufficiently large samples, the probability of observing or obtaining a sample for which p hat is less than this quantity here, p naught plus z sub alpha times the square root of p naught times 1 minus p naught over n. For sufficiently large samples, that probability will be approximately equal to 1 minus alpha. And so by the complement rule, the probability that we observe a value of p hat greater than that quantity is going to be approximately alpha. And so we can use that. Again, we're going to partition the sample space of p hat into two sets. One being the set of values that are consistent with the null hypothesis and therefore lead to the acceptance of the null hypothesis, or again, we would usually say that we would fail to reject the null hypothesis, or values of p hat that are in this set. And the other part, the other piece, the other part of that sample space of p hat containing values of p hat that are inconsistent with the null hypothesis. Values of p hat that are greater than, or they're on the interval here from p naught plus z sub alpha times the square root of p naught times 1 minus p naught over n up to 1. And so these are values of p hat that are inconsistent with this null hypothesis, all right, and therefore lead to its rejection at a significance level of alpha. And again, we can restate this in terms of decision rules, action rules. So we would accept or fail to reject the null hypothesis if p hat is less than or equal to this critical point, and we would reject the null hypothesis and conclude that the alternative hypothesis is true, again, at a significance level of alpha, if the observed value of p hat exceeds or is greater than that critical point. So let's put this all together, summarizing everything and putting it into a framework for decision making. So again, the sampling framework here is that we are performing binomial sampling as described. We have the same three types of hypothesis tests, or hypotheses that we can test. A two-tailed test, where the null hypothesis is that the population proportion is equal to a particular value, a hypothesized value, versus the alternative, which says that the population proportion is not equal to that hypothesized value. The left-tailed test, the null hypothesis being that p is greater than or equal to some hypothesized value, against the alternative that p is less than the hypothesized value. And then the right-tailed test, where the null hypothesis is that the population proportion is less than or equal to a hypothesized value, versus the alternative, which says that p is greater than the hypothesized value. So a two-tailed test, a left-tailed test, and a right-tailed test. And so we can use p hat as the test statistic, as we have been. That's the way we've been looking at this so far. And so if we were to use p hat as the test statistic, then for sufficiently large sample sizes n, the sampling distribution of p hat, if the null hypothesis is true, is normally distributed with a mean of p0 and a variance of p0 times 1 minus p0 over n. If the alternative is true, then it'll still have an approximate normal distribution, but the mean will be different than p0. And in particular, it'll be equal to p, whatever p actually is. And also the variance of p hat will be different than p naught times 1 minus p naught over n. It'll be just p times 1 minus p over n, whatever p happens to be. And so using p hat as the test statistic, if we're performing a two-tailed test, we would reject the null hypothesis if p hat is less than this critical point, or if p hat is greater than this upper critical point. If we're performing a left-tailed test, then we're going to reject the null hypothesis for small values of p hat, in particular values of p hat that are less than this lower critical point. And if we're performing a right-tailed test, then we will reject the null hypothesis for large values of the test statistic, in particular values of p hat that are greater than this upper critical point. Now, typically, as is usually the case, we would use a standardized version of the test statistic. Although we use the unstandardized version, p hat, in thinking about, and coming up with intuitive approaches to testing, and from there we came, we came up with a rigorous way to come up with critical points. Even though we use that unstandardized version p hat to do that, once we come up with this, then we would typically standardize everything so that expression of the critical points, calculation of the critical points, is easier in that case. So if we choose to use the standardized version of the test statistic, we'll call it zcalc, because under the conditions of the null hypothesis, that test statistic is approximately standard normal. And so again, we have here the formula for the standardized version. And if the null hypothesis is true, then the sampling distribution of this test statistic will be approximately standard normal, as we've said. And this approximation should be pretty good for large values of n. And it'll get better and better for larger and larger sample sizes. If we have a small sample size, we probably wouldn't want to use this procedure at all, because this whole procedure, as you now know, is based on the normal approximation to the binomial distribution. And so if the sample size is not large enough for that approximation to be adequate, then we would not want to use this procedure at all. We would want to find some other procedure, and there are other procedures. But again, in those cases where we do have a large sample, this is a perfectly good procedure to use. And so again, if we're using the standardized test statistic, then the rejection criteria for a two-tailed test would be to reject the null hypothesis if the standardized version of our test statistic, z-calc, is less than negative z sub alpha over 2, or if our test statistic, z-calc, is greater than positive z sub alpha over 2. So again, we've got two critical points, the lower critical point and the upper critical point. But for a one-tailed test, we only have one critical point. For a left-tailed test, the rejection criteria is to reject the null hypothesis if the standardized version of our test statistic, z-calc, is less than negative z sub alpha, and if we're performing a right-tailed test, then the rejection criterion is to reject the null hypothesis if z-calc is greater than positive z sub alpha. And then we have formulas for the p-values. And so if we are performing a two-tailed test, then the formula for the p-value is twice the probability that a standard normal random variable is greater. Actually, this should be greater than or equal to. Let me fix that real quick. Okay, so that's been fixed. So make sure that you make that fix in your notes. So again, if we're performing a two-tailed test, then the p-value for that test is 2 times the probability that a standard normal random variable is greater than or equal to the absolute value of the test statistic z-calc. If we're performing a left-tailed test, then the p-value is the probability of that a standard normal random variable is less than or equal to the observed value of z-calc. And if we're performing a right-tailed test, then the p-value is equal to the probability that the standard normal random variable is greater than or equal to the observed value of z-calc. And so these p-value formulas should look very familiar to you because these are the same p-value formulas that we used, for example, in testing hypotheses about a population mean using a z-test. So let's look at an example. And so an advertisement claims that more than 60% of doctors prefer a particular brand of pain medication. An agency established to monitor truth in advertising conducts a survey consisting of a random sample of 120 doctors. Of the 120 doctors, 82 indicated a preference for the particular brand. Is the advertisement justified? Test using a significance level of alpha equal to 0.05. And so let P denote the proportion of doctors who prefer this particular brand of pain medication. Note that the claim made in the advertisement will be true if and only if P, the proportion of doctors, and again I'm stressing proportion here as different than the percentage, right? And so we're going to state, even though the claim is stated in terms of percentages, we're going to translate that into a statement involving proportions because that's how the hypotheses are represented. So note that this claim will be true if and only if the proportion of doctors who prefer this particular brand of pain medication is greater than 0.6. And so that is what we're trying to see. Is there sufficient evidence to be able to make that claim? And so that is the statement that goes in the alternative hypothesis. All right. So remember that we put what we're trying to show in the alternative hypothesis. Is there enough evidence to show a particular claim or statement or conclusion? Then that is what goes in the alternative hypothesis. The opposite of that would go in the null. And so the hypotheses are the null hypothesis being that the proportion is less than or equal to 0.6, and the alternative is that P is greater than 0.6. Because this is a right-tailed test, right? It's a right-tailed test. The inequality is pointing to the right in the alternative hypothesis, and we're supposed to use a significance level of 0.05. And so then the rejection criteria is to reject the null hypothesis if z-calc is greater than the upper fifth percentage point, of the standard normal distribution, which is 1.645. Now, the sample proportion, the proportion of doctors in the sample who prefer this particular brand of pain medication, is 82 over 120. And so the test statistic is therefore z-calc equal to p hat minus p0 over the standard error of p hat if the null hypothesis is true. And so if that's the case, then the standard error of p hat would be equal to the square root of p naught times 1 minus p naught over n. So we have the sample proportion, 82 over 120, minus the hypothesized value of p, which is 0.6. And then, again, notice that we're using the hypothesized value, 0.6, down here in the denominator in calculating the standard error p hat. So to 3 decimal places, this test statistic is equal to 1.863. And because that is greater than the critical point, 1.645, the rejection criteria have been met, and so therefore we reject the null hypothesis and conclude that p is greater than 0.6. And so we can conclude then that there is sufficient evidence at the 0.05 level of significance to conclude that the proportion of doctors who prefer this brand of pain medication is greater than 0.6. Equivalently, we then therefore conclude that the percentage of doctors who prefer this particular brand of pain medication is greater than 60%. So at a 0.05 level of significance, there is the claim is warranted. Now, let's instead of using the the test statistic and critical point method, we could use the p-value approach. And so because this is a right-tailed test, the formula for the p-value is the probability that the standard normal random variable z is greater than or equal to the observed value of the test statistic, which was 1.863. And because z values are, in the standard normal table, the z values are given to only 2 decimal places. I'm just going to round. We could maybe interpolate, but I'm not going to do that for the purposes of this problem. It suffices just to round the observed value of the test statistic z-calc to 2 decimal places. And so this p-value is approximately equal to the probability that z is greater than or equal to 1.86, which from the standard normal table is 0.03144. And because that value is less than or equal to 0.5, we would reject the null hypothesis and conclude that p is greater. And again, when we say p, this is the population proportion. We're concluding that the population proportion is greater than 0.6. So that is how we use how we test hypotheses about a population proportion. If you think about it, the steps involved in the hypothesis test, the same type of steps are performed in this framework, in this particular testing situation, as they were for the other testing situations as well, whether we're testing hypotheses about population variances or testing hypotheses about population means. The steps are the same. The only differences are in the formulas for the test statistics, and the sampling distribution depends on the situation as well, but the overall steps are the same. Now, what would be the conclusion? Let's think about this. We said that at a 0.05 level of significance, there is sufficient evidence to conclude that more than 60% of doctors prefer this brand of pain medication. So the claim is warranted at the 0.05 level, right? But what would happen? What would be our conclusion at the 0.01 level of significance? Well, we know we've calculated the p-value. We know that the p-value is 0.03144, and because that is not less than 0.01, we would fail to reject the null hypothesis at the 0.01 level of significance. So while there is sufficient evidence to reject the null hypothesis and conclude that p is greater than 0.6 at the 0.05 level of significance. At the 0.01 level of significance, there is insufficient evidence to conclude that the proportion of doctors who prefer this brand of pain medication is greater than 0.6. So you see that the conclusion that we draw depends on the level of evidence that is required in order to reject the null hypothesis. And that level of evidence required is encapsulated by, contained in, related to, or dependent upon the significance level that we use for the test. And you can see here, that the general statement that we make, that if you use a smaller level of significance, then you are demanding more evidence against the null hypothesis, and this demonstrates this. There is sufficient evidence at the 0.05 level, but there's insufficient evidence at the 0.01 level in this case. So the claim would be warranted at the 0.05 level of significance, but it would not be warranted at the 0.01 level of significance. All right. Okay, now let's look at constructing confidence limits and two-sided confidence intervals for a population proportion. And so again, we're going to be basing our construction on the approximate sampling distribution of this estimated standardized version of p hat. So here we have p hat minus p over the estimated standard error p hat, which is the square root of p hat times 1 minus p hat over n. And we know for sufficiently large sample sizes that will be approximately standard normal. And so it follows that the probability of observing a value of the standardized version of p hat less than or equal to z sub alpha is approximately 1 minus alpha. And so then we can rewrite the expressions here inside the parentheses to get p all by itself. And so the probability that we get a hold of a sample for which the observed value of p is greater than or equal to this quantity computed from the sample is 1 minus alpha. And so this implies that in repeated sampling, the random variable p hat minus z sub alpha times the square root of p hat times 1 minus p hat over n will be less than or equal to the true population proportion p approximately 1 minus alpha times 100% of the time. And therefore, the population proportion p will be greater than or equal to this random variable, this same random variable, approximately 1 minus alpha times 100% of the time. And so for this reason, we call the random variable given by this quantity here a 1 minus alpha times 100% lower confidence limit for p. Now, once we've calculated this, once we've obtained the sample and calculated that lower confidence limit, the way that we interpret this, we say that we are 1 minus alpha times 100% confident that the true value of p, the population proportion, is greater than or equal to this lower confidence limit, because it was constructed using a procedure which had a probability of 1 minus alpha of coming up with a quantity that was less than or equal to p. We can also come up with an upper confidence limit by looking at this probability statement, and from it coming up with this quantity. So based on this probability consideration, the probability of getting a hold of a sample for which p hat plus z sub alpha times the square root of p hat times 1 minus p hat over n is greater than or equal to the true population proportion p, that probability is approximately 1 minus alpha. And so that means that in repeated sampling, the random variable given by p hat plus z sub alpha times the square root of p hat times 1 minus p hat over n will be greater than or equal to the population proportion p, approximately 1 minus alpha times 100% of the time. And so therefore, the population proportion p will be less than or equal to the random variable p hat plus, again, the same quantity, p hat plus z sub alpha times the estimated standard error p hat, approximately 1 minus alpha times 100% of the time. And so we call that random variable a 1 minus alpha times 100% upper confidence limit for P. And again, once we have our sample, once we've calculated this upper confidence limit, to interpret this, we say that we are 1 minus alpha times 100% confident that P is less than or equal to this upper confidence limit. And then finally, to construct a two-sided confidence interval for P, we construct a 1 minus alpha over 2 times 100% lower confidence limit for P, and a 1 minus alpha over 2 100 times 100% upper confidence limit for P, and then we put them together, and that gives us a 1 minus alpha times 100% two-sided confidence interval for P. And so once we have constructed this from a sample, we say that we are 1 minus alpha times 100% confident that the true population proportion, whatever it happens to be, is somewhere in this interval, somewhere between these two endpoints. So let's look at another example. In a pre-election poll using a random sample of 150 voters, 84 favored candidate Smith. Construct a 95% confidence interval estimate of the proportion of voters in the overall population that favor candidate Smith. So our point estimate of P, the proportion of voters who favor candidate Smith, our estimate of that is P hat equal to 84 over 150, which is 0.56. And so we're constructing, in this case, a two-sided confidence interval, a 95% confidence interval estimate of P. And so that's going to be given by our point estimate, P hat minus plus the estimated margin of error of P hat, which is Z sub alpha over Z sub 0.025, the upper 2.5th percentage point of the standard normal distribution, times the estimated standard error of P hat, which is the square root of P hat times 1 minus P hat over n. So we have 0.56 minus plus 1.96 times the square root of 0.56 times 0.44 over 150. And so we get an interval that has endpoints 0.481 and 0.639 rounded to 3 decimal places each. And so to interpret this, we would say that we are 95% confident that the proportion of voters who favor candidate Smith is somewhere between 0.481 and 0.639. If we wanted to convert this to percentages, we could. We could say that our point estimate for the percentage of voters that favor candidate Smith is 56%, and that we're 95% confident that the percentage of voters who favor candidate Smith is somewhere between 48.1% and 63.9%. Okay, so what if we are in the planning stages of an experiment where we are going to be collecting data from which we're going to calculate a confidence interval, and that we would like the margin of error to be no more than a specified amount? So what sample size would be required in order to do that? What would be the smallest sample size that would satisfy that criterion? And so that is what we're looking at here in this slide. Now the margin of error for a 1 minus alpha times 100% confidence interval estimate of a population proportion is given by this quantity here. Now let me back up a second to the previous slide. Again, this was the margin of error for this interval. So I'm just going to denote that by E. Now, let me just point out here that this is actually the true margin of error because we don't have hats on the P here. On the previous slide, I called this quantity the estimated margin of error of P hat, and it's estimated, and we have to use the estimated margin of error in this particular, or when we're constructing a confidence interval, because we don't know P. We don't have a value to plug in here. All right, but when we are coming up with this formula, we're just going to go, we don't have a P hat, we don't have a sample yet, right? We're in the planning stages, and so we're stuck with using P. So this is actually the true formula for the standard error, for the margin of error of P hat. And so if we take that and we solve that expression, that equality, if we solve that equation for n, then we get this sample size, z sub alpha over 2 squared times p times 1 minus p over e squared, where e is it represents the desired maximum margin of error allowable. Now, again, we want to come up with a value of n that we can use to then select our, when we select our data, when we select our sample. But notice that this formula for n depends on p, which is unknown. P is the value that we're wanting to estimate using a confidence interval. And so we don't know it. And so we can't, with that there, we can't calculate this exact sample size. Now, what we can do is come up with a conservative upper bound on the sample size. It's conservative in the sense that the sample size that we come up with will guarantee that the margin of error is no more than the maximum allowed. And that the margin of error of the confidence interval will be no greater than the maximum allowed. And so we do that. We know we can come up with this conservative upper bound for the sample size by noting that for a fixed value of alpha and for a fixed value of e, this expression obviously would then be a function of p and a function of p alone, and that the maximum value of this expression is obtained when p is equal to 1/2. All right, and so what we would do then to get this conservative value of the sample size is use p equal to 1/2 in this expression. So we would have 1/2 times 1 minus 1/2, or 1/2 times 1/2, which is 1/4. And so then we would use that, and that would give us a value of n that we can use, for our sample size. And so that's where the 4 comes from in the denominator. All right, we're using the most conservative value of p, in this expression, in the sense that the margin of error that we eventually obtain, if we use this sample size, then the margin of error that we obtain once we collect our sample and calculate the confidence interval, and in doing so getting the margin of error will be no more than that which is required, or that was which was specified. And so let's look at an application of this in close elections between two candidates. In other words, where p is close to 0.5, where p is the percentage of the proportion of voters who favor a particular candidate, maybe we say candidate Smith again, then a pre-election poll must give rather precise estimates to be useful, right? It doesn't do anybody any good, any decision makers, any strategists any good, if the margin of error is too large, right? Having a confidence interval ranging from 0.4 up to 0.6, or 0.35 up to 0.55 or something like that is really no good. It's just the interval's too wide. What we would want is a confidence interval that has a margin of error that is very, small, fairly small enough to be useful. And so suppose that we would like to estimate the proportion of voters favoring a certain candidate using a 95% confidence interval, but where the margin of error is no more than 1%. So we want to have a high level of confidence in the interval, a high level of confidence that the interval actually contains the proportion of voters who favor the candidate, but we want the interval to be narrow enough to give us really precise information. And so in this particular scenario, we would want the margin of error to be no more than 1%. And so what sample size would be needed for that? What is the smallest sample size that would guarantee that? Now, what if a margin of error of 3% would suffice? What sample size would be sufficient for that? What would be the smallest sample size that would guarantee a margin of error of no more than 3%? Well, we can use the formula from the previous slide to come up with those sample sizes. And so let's take a look. And so if we require that the margin of error is no more than 1%, in order to guarantee a margin of error of no more than 1%, the required sample size would be given by this formula. So again, we're constructing a 95% confidence interval, and so the interval coefficient, the z-value, is 1.96. And remember, don't forget, we've got to square that value in the numerator. The value of E is 0.01. Remember, the margin, the E is the margin. I'm sorry, yeah, the required or the upper limit on the allowable margin of error that we want. So we want that to be no more than 0.01. So E is 0.01. And again, we have to square that, so be careful to do that. And so if we plug in those values and evaluate it, we get a sample size of 9,604. Now, that seems like a large sample size, and it really is. But when you consider that we've not said anything about the size of the population, this procedure could be used. If we were talking about, for example, a presidential election, and so there are millions and millions and millions of voters. So this is a very small proportion of the overall voting population. And so we could come up with, using this relatively small sample size, we could come up with a confidence interval for the proportion of voters who favor candidate Smith that has a 95%, for which we have 95% confidence, and for which the margin of error is no more than 1%. So we could come up with, an interval that has a width of no more than 0.02 percentage points. So this is a fairly small sample size when you think about the size of the entire population. However, from a practical standpoint, from the standpoint of actually conducting, a poll and getting this many respondents, especially in a short amount of time, that is a large sample. So perhaps a 3% margin of error would suffice. And so if that's the case, then what is the smallest sample size that would guarantee a margin of error of no more than 3% while still maintaining that 95% confidence level? And it turns out that the smallest sample size that would guarantee that is 1067.1, the ones repeating. And because there's a fractional portion, then we would go to the next larger integer, which is 1068. And so, again, using a sample size of 1068, then we would be able to estimate the proportion of voters who favor a particular candidate at 95% confidence with a margin of error of no more than 3%. Now, let me just say a few words about this process of estimating a population proportion. The examples that we've been looking at here are about estimating the proportion or the percentage of voters who favor a particular candidate. And this is very appropriate for us to be talking about this because we are in the midst of a presidential election. And what we're seeing in the news is it appears that the polls were very, very wrong in many cases. And the people in the news and the pundits, they're reminding us that the polls were very wrong in 2016 as well. And so let me just say a few words about this. It can be discouraging from the standpoint, well, it's really from anybody's standpoint, it can be discouraging when these types of polls appear to be inaccurate, and as inaccurate as some of these are. Let me just say that the results that you get from a procedure are only as good as the data that you are applying those procedures to. And as a statistician, one has to know, whether or not you have to be careful And if you have any kind of if you're not confident that your data are accurate, if your data are not biased, then you need to be very careful about coming up, using any kind of a procedure and coming up with results. And so, that is not just for statisticians, that's for anybody, any decision maker who is using statistical techniques, using statistical models or whatever. And so the results that you get, even though you may have a great model or a great methodology, if the data that you have are not if it's not a random sample or if they're not unbiased, if the quality of the data is questionable, then you really need to take a step back and think about whether you want to go forward. Because if you've got bad data, no model is going to give you a good result. Okay, that's the bottom line. And so, it's very possible, for example, in this current situation, uh, these polling outfits are relying on uh, automated phone calls to people, perhaps their cell phones. Uh, some polling outfits may call landlines, but as you know, many people these days don't have landlines, and there are probably differences in age groups whether people have landlines or cell phones and things like that. And so we need to be, you need to take those kind of things into consideration. And it's very possible that because of the current situation, we have a very polarized society. And some people are distrustful of the media. So many people are distrustful of polling outfits. And so it may very well be that people are refusing to respond to polls in the first place, or maybe maybe they're not telling the truth. Maybe they're not giving accurate information about who they would actually favor, or what their intentions are for a variety of reasons. And so my guess is that is one of the big reasons why many of these polls seem to be very inaccurate. Uh, Again, the methodologies are sound, but even if you apply a sound methodology to bad data, then you cannot really have confidence that you're going to get a good result. So, I would urge you to use this as a good lesson, in your own scientific decision making. Make sure that you perform your experiments in such a way that you have high quality data that is unbiased and that is randomly selected, randomly generated, and so that because those are the kinds of things those are the assumptions that are upon which these methodologies are based. All right. So again, you can have the best model in the world. You can have the best methodology in the world, but if you're applying it to bad data, then you cannot expect to get reliable results. So that is the end of this particular section, and in fact, it's the end of the module on inference procedures for a single population. And so after this, we're going to be moving into the last module in the course on inference procedures for two populations.